Thank you. Hi, my name is Michelle. I am working with Carlo Contaldi in the theoretical group in the physics department at Imperial College London. I'm currently an MSc student, so I'm completing the research portion of my degree. And to give some background, so we use gravitational waves to inform our understanding of fundamental physics. In particular, we know that our theory of gravity is incomplete and it's due to breakdown at high energy scales, like we've seen from measures of gamma ray bursts. And also, of course, with the familiar very short scales of quantum mechanics. So what my group is working on is trying to find the way that gravity could be reconciled as an effective field theory. And we do this by studying gravitational wave signals as they propagate in the weak regime. And in particular, we try to modify these signals to see if we can find any frequency domain effects and use those to constrain parameters. So gravitational waves we use binary black hole systems are really exciting because they can inform a lot our understanding of the universe. We can measure the acceleration and try to reconcile the cosmological constant and the Hubble parameter. They can provide experimental evidence for new classes of objects, which they did I guess 2 years ago. That might be a bit out of date now. And they can tell us about metallic and element compositions in other galaxies. But what we do in the group I work in is we use them to test general relativity. So my research in that context is we set up a dispersion relation. You can see it on the right here. And we work in the familiar FRW metric. We define a luminosity distance, and we also compare it to a modified luminosity distance. So we use these, I'll call them alpha and A parameters to modify the gravitational wave signals. And in particular, we work with the pi CBC waveforms, which I think a lot of you are familiar with. I've heard them brought up in a couple of talks. And this library is very useful for looking at LIGO signals. And in particular, what we do, I guess what I do in my research is I generate waveforms using their phase and amplitude definitions, and I try to recreate the waveforms that we can find in pi CBC. And then once we've convinced ourselves with those, we then go in and add the phenomenological parameters to have the modifications I spoke about earlier. We do this by assuming, should actually play that, by assuming a stationary phase approximation. And we use that to describe the wave propagation. And it's important to note that the modified terms correspond to Lorentz violating theories of gravity. So different values that these parameters take on. For example, alpha goes anywhere between 0 and 4 in steps of 1/2. And each of those corresponds to a different effective field theory. So the idea here is to take a phenomenological approach to set up a general theory, and then to look at what those parameters correspond to in known effective field theories and see if any of them make sense for the signals that we get. You can see on the right, so we have the familiar GR phase term, and then we have a modified phase term. And you can see a plot of the amplitude and the frequency space. So the idea here is to start with a theoretical derivation. So I have, you'll see the modified luminosity distance. So it looks a lot like the familiar luminosity distance we're all used to dealing with in cosmology. That is then implemented in Python. We can plot the results to see how different values of the phenomenological parameter affect this luminosity distance by looking at the ratio. And then we can output some sort of modified signal waveform that should look a lot like the LIGO signals. And the important thing here is we will look at like high and low pass filters because a lot of these effects are very small. So we have to either plot the ratios of the modified waves to the regular waves or look in certain filters that can tell us a lot, but that might not correspond to very physical situations. So when we talk about developing this phenomenological model, the idea is to study the modification systematically. because it's very well and good to take one waveform signal, pass it through, modify it, and try to find something. But what you really want to do is build robust statistics that will help you constrain the parameter space. So when we pass through the waveform signals, the first thing is to use a Fourier transform to put it in the frequency space. That's done because then the noise will be stationary with respect to the domain. We look through the machinery by defining all of the parameters. This includes things like the chirp mass and the luminosity distance, or the inclination angle of the system, but it also involves looking at the phenomenological parameters I mentioned earlier. So you can see them there. This is used to output a modified signal, which is a product of the amplitude and complex space term. It's important here to mention that one thing we did was we tried to sort of just put through a reduced phase term. So as a result, we would lose the complex information there. So we had to modify the inner product that we used to prevent losing that important information. And then finally, we compare this to the original, and we do it for a whole set of input waveforms. And this is done using a Fisher analysis. So I'll talk about that in a moment. So importantly, we look at frequency dependent effects. The reason for this, as I said earlier, is because it keeps the noise stationary. So we can just use the simple noise power spectrum. And this allows us to also study signals from LIGO and LISA. So of course, we don't have the signals from LISA yet. We hope to incorporate those once they're available, but we want to build out the machinery ahead of time so we kind of know what to expect. You can see the image on the right, which I took from a white paper from LIGO. You will see different characteristic strains of gravitational waves. And very conveniently, sort of, you have a few that go through the frequency bands for both LISA and LIGO. So this tells us something very important. We can look at these waves without any sort of electromagnetic counterpart, and we can still have multiple detectors looking at signals from the same objects and informing our understanding of how they actually propagate to us. So the intuitive thing here is to say, we observe in one frequency band. It depends which way your dispersion relation is going, which one you will see first. And you introduce these modifications like we've said, and then you have sort of this expected value of we think we will see this effect, and then you go into the other detector and you're actually able to say, yes, we do in fact see that. So it's very exciting because when we're able to observe with different frequency bands, we can actually use observations to confirm those modified theories. Yes, so what I mentioned earlier about generating a Fisher matrix, it's actually what I'm working on now. So I was very hopeful to have that done before the presentation today, because then I could show you some exciting results. Unfortunately, it's taking a bit more time than I expected. So yes, the idea there, I'll just say briefly, I'm sure a lot of people are familiar with how a Fisher analysis works. You work in your parameter space and you say, you have your likelihood, and you have basically this maxima point where the sum of the second order partial derivatives is 0, and you have your eigenvectors corresponding to eigendirections, and you can think of it as sort of you go down in slope along those eigendirections, and that tells you how much the parameter space varies with each parameter. So this is very useful, of course, because it allows us to see which parameters are degenerate with respect to each other. So maybe something like inclination angle and one of the phenomenological parameters will actually be completely degenerate, and you wouldn't be able to see any sort of effects in one without the other. So that's going to be hopefully very exciting. And the next steps would be, once that is complete, to incorporate objects such as emeries and to consider first order effects from geodesic path deviations. Right now, we're sort of ignoring those higher order effects. So I believe that's most of my time. If anyone has questions, you can also find my code and some more details on my GitHub, which I have here. And otherwise, I'm happy to respond to any questions.
Okay, while I give anybody a chance to write up a question, I will just say I think analysis taking a little bit longer than we had hoped is probably quite familiar to a lot of people in this meeting. So I think you have our sympathies there. Any questions from the audience? All right. I guess one from me then. So what, how do you expect this to, this sort of work to affect the analyses which we're doing at the moment with LIGO? I mean, do you expect to, do you expect it to be important with the kind of sensitivity that we have at the moment?
Yeah, so I guess one thing I did mention is potentially including observations from the Einstein telescope, which will have sort of better sensitivities for the same frequency band as LIGO. The idea here is that with the sensitivities we're currently working with, we should be able to see these effects just from the observations from LIGO. Of course, the more data you have and the better sensitivity, the better your signal to noise ratios will be. But in sort of the preliminary things we're seeing, we should be able to use the sensitivity from LIGO.
Okay, great.